I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on uniform circular motion and centripetal acceleration. In this series of videos, we're going to talk about uniform circular motion. In this video specifically, we're going to address centripetal acceleration and what that means and what uniform circular motion means. So an object that has uniform circular motion means that it's moving at a uniform speed or a constant speed, and the radius doesn't change either. So it's moving in a perfect circle and the speed doesn't change. Now, uniform circular motion is accelerated motion, and we're going to answer that question as to why and how it is accelerated motion. So let's say, for example, you have an object that you're spinning over your head in a clockwise circle. And here's an overhead view. Let's say at that moment in time that's pictured, the string breaks. And the question is, in which direction will the object move after the string breaks? So picking one of the paths A, B, C, or D, D being continuing the curve. So think about this for just a second. If you answered C, you're correct. The reason for this is that objects that are moving in a circular path are moving tangent to that circular path, meaning that the arrow that represents the speed would just be touching the circle. So this is important to know because what we're going to do is we're going to construct a motion map for our object that's spinning in a circular path. So the velocity is tangent to that circular path. So knowing that the velocity is tangent to the circular path, what we're going to do is we're going to draw velocity vectors all the way around our circle to start our motion map. So remember, a motion map represents motion by time, positioning, the velocity, and acceleration. So where we place the vector is important. And we also know that it's moving at a constant speed. Since the speed's constant, that means all the velocity vectors are going to be equal length. They're all going to be drawn tangent, and it's going to go all the way around the circle. And we could continue going around the circle over and over and over again. But we're just going to look at one rotation. The question is the velocity constant as well? And based on what we know about velocity, it depends on both speed and direction. And since the direction is changing, no, the velocity is not constant. That means there's an acceleration. So that answers the question is, why is uniform circular motion accelerated motion? Well, because the velocity is changing direction. So we know that acceleration is change in velocity over change in time, which means we can take a second velocity minus a first velocity, divide that by the time. The problem is if we use numbers, that would give us 0. So what we're going to do is we're going to apply v2 to be one of these vectors and v1 to be another one, and I've labeled those on the diagram. Now v2 minus v1 can also be written as v2 plus the negative of v1 over delta t. What we're going to have to do to find the change in direction of the acceleration is we're going to have to do something called vector addition. Now, vector addition means that we're going to draw a picture of the vectors. So what we're going to do is we're going to take one of our vectors, the first one in our equation, which is v2, and we're going to reconstruct it off to the side. Then we have the negative of v1. The negative just means it's going to point the opposite direction. Now to add vectors, a vector has two ends. It has a tail, which is the beginning of it, and it has a tip, which is the arrow side of it. To add vectors together to draw a picture, to add them graphically, we take the tail of the second one, negative v1, and put it to the tip of the first one. And this is how you would draw a picture or a graphical representation of the vectors being added together. Now, the result of adding vectors is called the resultant vector, which is drawn here. You start at the beginning of v2 and you go to the end of negative of v1, and that represents our change in velocity. Now, acceleration isn't just dependent upon change in velocity, it also depends on change in time. So we're going to use our motion map and we're going to place the change in velocity vector over a period of time, the average of v2 and v1, which would be right in the middle, and that would represent our average change in time. So here is our acceleration vector, a change in velocity over a change in time. Now we can repeat this for each pair of vectors, and we can see that each pair of vectors we do the vector addition for, and we put it in the midpoint between the two vectors. And you're going to start to see a pattern as to where the acceleration vectors are pointing. And if you noted that the acceleration vectors are pointing towards the center, you're correct. Each of the velocity vectors is tangent. The acceleration vectors points towards the center. You might notice something else about the velocity vectors and the acceleration vectors and how they're oriented. They're perpendicular to each other as well. So the acceleration vectors all point towards the center. So we're going to break a word down: centri, which is Latin for center, and petal, which is Latin for go to or seeking. So putting that together, centripetal, and applying that to acceleration, centripetal acceleration is a center-directed or center-seeking acceleration. And as you can see on the motion map, the acceleration is pointing towards the center. So the object is seeking the center. It's never going to reach the center. It's just changing direction towards the center of that circular path. So let's go ahead and recap our motion map. So first off, the velocity vectors are all drawn the same length with the uniform speed, and they're drawn tangent to the circular path. We also know that the acceleration vectors all point towards the center of the circular path and are perpendicular to the velocity vectors. So those are the important points that you need to know for drawing a motion map. And the good news is the motion maps are always the same for uniform circular motion. It might just be a portion of that circle if a car is going over a hill or down a hill. It would just be the top portion or the bottom portion of that. So let's rely on some of your experiences of being in a car. So when a car accelerates, as it speeds up, you as a passenger feel like you're flung backward. You're thrown back into the seat. But you're not really thrown back. What's happening is your inertia is resisting that acceleration. You want to stay still. Your body wants to remain stationary. So because you want to remain stationary, your body feels like it's flung backwards and it wants to remain stationary. So as the car speeds up, you go flying towards the back. When a car decelerates, it slows down, you feel like you're flung forward. You're going towards the dashboard. And that's not that you're flung forward, just your inertia resists the negative acceleration. You're not flung, it's just your body wants to stay moving at a constant speed. So when you slow down to a stop, you feel like you're flung forward. Now, when a car makes a left-hand turn, if you make a sharp left-hand turn, you feel like you're forced outward to the right. You're towards the outside of that circle. But that's not you being flung. That's just your body resisting the change in velocity. Your body wants to continue in that straight line. So your body does continue in a straight line by leaning to the right side. So if we look at acceleration as a general rule, relying on your experience, whenever you feel flung in a certain direction, that means the acceleration is pointing in the opposite direction. So we've looked at 3 examples of 2 in linear and 1 in circular. And you might remember we did this with some elevator problems back in the forces unit. And when you're flying upward, that means the elevator is accelerating downward. And when you feel like you're sinking down into the floor, that means the acceleration is upward. So relying on your experience to figure out the direction of acceleration. It is always towards the center of a circular path. So this is centripetal acceleration and how it relates to uniform circular motion. I hope this was helpful, and I hope you have a great day and an even better tomorrow.
If you found this video helpful, don't forget to click the like button down below and subscribe to my channel, Cavi Coaches, and follow me on Instagram and Twitter @Cavi Coaches.